All right. Hello, everybody. Thank you for coming to the webinar today, first one of the year. Just a couple of things like usual. This is being recorded. The slides and the recording will be distributed by end of the week for you to have and will also be up on our website. If you have any questions during the webinar, please feel free to throw it in the Q&A, the chat, or raise your hand at the end. We'll be sure to get to your question and get that answered. With that, I will hand it over to Christopher.
Thank you, Kate. Welcome, everybody. Good afternoon, and thank you again for joining today's webinar for the Gas Emerging Technologies program. My name is Christopher Salerno, Engineer 2 at Linkus Incorporated, presenting on behalf of our project team. Today, I'm pretty excited to finally present the results on our hydronic fluid additive study, primarily energy savings and commercial hydronic heating systems, which was conducted under the statewide Gas Emerging Technologies program, jointly led by SoCalGas and ICF. The study was performed at 2 representative Northern California commercial office buildings, and today's presentation, we will detail the findings and then the recommendations that resulted from the study. So before beginning, I would like to acknowledge the guidance provided by the GET program team at SoCalGas and ICF, particularly Stephen Long, along with the anonymous manufacturer's technical guidance of the hydronic fluid additive during the installations. Also, as a disclaimer, this project was funded by the California utility customers under the California Public Utilities Commission, the CPUC. And the findings that I'll report today reflect specific conditions observed at each test site. So there's no warranties or guarantees, and this should not be interpreted as a universal performance guideline. So before going into the presentation, I'd like to outline and provide a clear technical roadmap with today's agenda. So the presentation is structured as follows, beginning with the executive summary, which highlights the overview of all the key findings. And then we go into the technology description of the additive and how it works and its operating principles. Then into the assessment methodology, specifically the type of field study that was implemented to provide the savings. Then we go into the site descriptions and characterizations, and then to the installation details for each site. Then we go into a baseline energy analysis used from data collection and to characterize the energy consumption at each site. And then we go into the post-installation analysis. Then go into the shift to an OAT binning method, which is an alternative savings method, which we'll see is due to poor modeling fits, which we'll go into more detail into later slides. Then we will go into the actual results, and then go into the quantified savings results and customer survey outcomes. Then go into the surface tension results, was measured as part of the study. And then lastly, discussion and conclusions and recommendations based on what was found based on the work. So to begin, I'd like to go over just an executive summary, which summarizes and highlights all the key findings into one slide. Again, each of these key points will be touched upon throughout the presentation. And so primarily, the primary objective of this study was to quantify gas energy savings. So again, there were 2 sites that were selected for this study based on recruitment. And so for site number 1, we can see the resulting gas savings was 10.7% using the International Performance Measurement and Verification Protocol, IPMVP for short, option C whole facility approach, also using a weather normalization. For site number 2, we found and concluded that there was a 19.8% gas savings using the IPM&V option B retrofit isolation approach due to the available data, and then also normalizing with heating load. And we'll go into more detail of what that is. Then for this, we conducted an independent third-party laboratory testing, showing that there was a 40 to 50% reduction in surface tension. Then we go into the material costs for the installation of the additive, which ranged from $5,050 to about $14,166 with installations completed without hot water service disruptions. Specifically, in terms of the payback, site number 1 preferred that the ROI be under 3 years for adoption due to the 10.7% savings. And overall customer satisfaction was moderate, showing some interest in implementing in other buildings. And again, there was no service interruptions during the installations of these, so it showed easy retrofit. And these results established measurable energy reduction in real-world hydronic heating systems. And it's recommended to do further studies in different varying climates to verify savings and varying temperatures. So to understand the mechanism underlying these savings, we will next describe the technology and then the underlying physical principles behind that. So going into the technology description of the hydronic fluid additive itself, this emergent technology is a chemical additive that's injected into a closed loop hydronic fluid additive, fluid of a hydronic heating system that has been showed to reduce energy consumptions. This is done by modifying several thermal physical properties, including a surface tension, which was measured as part of this study and used as a primary indicator of the additive effectiveness, thereby enhancing several heat transfer mechanisms by increasing the surface wetting, which is shown to the photo to the right, and which also results in preventing of bubble formations at the surface that act as heat insulation. So the resulting improvement in this heat transfer rates reduces the overall boiling cycle frequency and overall boiler runtime while satisfying the same heating demand and/or level of service, meaning that the boilers operate less while meeting the same heating demand due to the increased heat transfer rates due to the additive. The additive itself required no special modifications, hardware modifications, and is fully compatible with existing high-efficiency condensing hydronic boilers, as will be shown in the study. And with these operating principles established, we will now move on to the assessment methodology and how we have applied that to quantify the performance. So again, the main primary objective of this study is to verify manufacturer claim savings of the additive that lacked available source data to cross-validate those claims. So the primary objective was to assess real-world cost and market barriers, and then verify the claim savings of 7 to 15%. Again, the approach and the evaluation followed the IPM&V protocols, leveraging existing building automation system data, BIS for short, to leverage existing infrastructure and to limit metering requirements and to access available data over multiple heating seasons. So site number 1, again, utilized an option C whole facility metering, which is due to retrofit level metering issues, which we'll go into detail on a later slide. And then site number 2, as initially planned, followed the IPM&V option B, which is metering at the retrofit isolation level, that being the boilers themselves for this study. The activities included that we first performed an extensive outreach to recruit which was initially scoped as 3 sites, but due to the challenges in finding suitable sites with available data and sites that were willing to participate, it was found that only 2 sites were recruited at the results for the study. Once the 2 sites were recruited, we collected the baseline data, collected baseline samples for surface tension testing. We performed the additive dosing, then repeated monitoring across an additional heating season, then compared the performance, and then lastly assessed customer feedback with a short survey. So now we'll go into the site descriptions and then into the installation details associated with the additive itself. So again, the study only ended up recruiting 2 sites after an extensive outreach effort. Again, we were looking for sites that had working available BAS systems and also sites that were willing to participate in the study, given these were the first studies in California. And so initially, we wanted 3, but only got 2. Both sites were located in California in CZ03, which is the San Francisco Bay Area. For site number 1, consisted of 7 floors across 251,000 square feet. And it's an office building equipped with 2 million BTU per hour, 92% condensing fire tube boilers, which are actually shown down to the left-hand side. And those are serving 8 air handler units across the building. And then similarly for site number 2, is a single-story mixed-use office space building across 178,432 square feet, consisting of 3 2 million BTU per hour hydronic boilers. These are actually cast iron boilers, not fire tube, at 94%, also serving 8 air handler units. Data was collected at 15-minute intervals, except for the gas data used for option C on site number 1, which was 24-hour daily PG&E data. And then the 15-minute data was aggregated into daily intervals for the analysis. So going into the actual installation of the additive itself and then the associated real-world costs, you can see here that the table presents the 2 associated volumes required of the additive itself. This actually, the first column highlights what total system volume or what was used to determine the required volume itself. So the required volume for site number 1 was 27 gallons based on a total system volume. And this was performed in-house by the in-house technicians. As you can see on the right, this is for site 1. The in-house technician is manually dosing the systems. Again, this was done without disruptions to the hot water supply, so no shutdowns were needed. For site number 2, actually outsourced a water treatment company to install the additive itself. So the total system volume determined by that was actually determined by the flow rate, the nominal design flow rate of the hydronic heating system instead of the total additive itself. So that resulted in only 8 gallons for that. And the associated cost for site number 1 was about $14,000 again, and then site number 2 about $5,000. That results in about $500 per gallon. And so both customers noted that this is reasonable. But again, site number 1 preferred that there be incentives to promote an ROI less than 3 for adoption due to the 10.7% savings. So having characterized the test environments and implementation, we'll now go into the baseline energy models and then characterize each system using the BAS system data and then into the energy savings analysis itself. So initially, the approach was to leverage existing BAS data for each site over multiple heating systems, heating seasons to properly characterize the system. And so, as you can see here on the left-hand side for site number 1, the weekday baseline models for the daily gas energy and also the daily HHW, which is the heating hot water energy, which is the heating load output energy of the boiler system. And so you can see here that the highlighted in blue are the R squared goodness of fit metrics, showing that these baseline models follow a linear trend as expected. As we expect that there be more energy used at lower OATs, which are shown here in these linear trends. So the baseline BAS data was leveraged and was successfully used to characterize the systems, despite some metering challenges, which will be presented into the next slide. So for site number 1, we found that the water flow meter was faulty, providing thermal efficiencies greater than 100%. So this required a shift to using the whole building PG&E gas metering data, as it was found here. The gas metering data was not available for these sites, so for this site, so it was opted to switch to option C using whole building PG&E meter data. For site number 2, the gas metering issues revolved around the retrofit isolation gas meters on the boilers themselves. And so there were communication issues that led to loss of data. And unfortunately, we were able to use a gas flow regression using available firing rate data to be able to use regression imputation and then salvage the data within the missing gaps. So these conditions are representative of real-world verification efforts, and they definitely underscore the value of adaptable analytical methods based on what's available on site for the BAS data and what's considered reliable. So now that we've gone over the challenges in the baseline models, we can now go into the post-installation performance that we observed, and then the shift to an alternative savings method due to the metering issues shown here. So this slide shows the post-installation regression models for the gas energy on weekdays. As you can see here, the R squared values are much lower than the baseline values themselves, which is actually likely due to the heating systems acting more dynamically from the increased heat transfer rates. So essentially, the additive is allowing for condition zones to reach set temperatures faster and improved responsiveness to heating demand changes, instead of tracking more linearly with the OAT as shown with the baseline models. Also, what's not shown here are other metrics such as the coefficient variation of the root mean squared error, and then also normalized mean biased error are also not shown here, but those also did not meet the required goodness to fit metrics. So for those reasons, the post models were not used in the analysis. It was found that it was required a shift to an alternative savings method using OAT bending, which will be shown on the next slide. So due to the poor modeling fits in the post installations, we wanted to shift to an OAT binning method. This enabled a rigorous comparison under equivalent weather conditions in accordance with the ASHRAE guidelines, sorting data into 5-degree outdoor temperature OAT bins, OAT meaning the outside air temperature. So it is accounting for the local weather conditions and comparing pre and post on similar OAT conditions. And furthermore, the approach allowed for equal comparisons and then included additional normalizations for weather normalizations for site 1 and then heating loads normalizations for site 2. This approach isolated the additive's contribution effectively without the good fits for the post models, and it also revealed higher savings at lower OATs, less than 60%, which is what's to be expected, as increased heating demand is expected at lower OATs. Another reason why OAT was used as an alternative method is that typical uses patterns are increased hot water behavior at lower OATs is a typical trend that has been showed. So into the energy savings results themselves. Again, for site number 1, it was resulting in a 10.7 gas savings using option C method, and then also further normalizing for the weather using heating degree days. Heating degree days is a metric used to define to quantify the heating demand, defined as how many degrees a day's average temperature falls below a base temperature. For this study, the base temperature was selected to be 80 degrees, as this was the boiler lockout temperature for both sites. So the boilers would not operate above an outside air temperature of 80 degrees. For site number 2, the resulting gas savings was 19.8% using an option B method, and further normalizing using the heating load output, again quantified as heating hot water, or kBTU per heating hot water load. This was done due to the availability of the data, due to the option B data being available, and so we were able to use that to load normalize and compare pre versus post under similar operating conditions. So these savings align with the manufacturer's claimed savings of 17 to 15%, and they represent an independently verified performance for these commercial hydronic heating systems in mild California climates. And now we'll go into the customer surveys results that we collected, and then go into the conclusions instead, conclusions and discussion. So the structured survey was conducted with facility personnel at each of the sites. It was indicated that the installation was straightforward, and that there was no hot water service disruptions or occupant complaints. And this was also viewed as a low risk activity due to the ease of installation. Site 2 expressed specifically the likelihood to expand to other sites due to the 19.8% savings. However, site number 1 is unlikely to adopt without additional incentives due to the 10.7% savings. This was based on the preferred ROI of less than 3 years to be able to provide a reasonable payback. Regardless, both facilities still recommended this technology for other buildings, especially in mild to colder climates, where savings have shown to be potentially more based on the trend in the findings from the OAT bending analysis, which shows that there were higher savings at lower OAT bends, less than 60 degrees. Also, site number 2 mentioned that there are concerns about product lifetime, and that primarily concern about chemical degradation of the additive, and to determine if there's any impact on performance over the lifetime of the product. And so to confirm the primary thermophysical mechanism, we arranged independent surface tension testing, which we'll validate and show on the next slide. So surface tension was the only property that was actually measured as part of the study. But again, it should be noted that surface tension is not the only thermophysical property that this additive does alter or improve to increase the heat transfer rates. However, it was used as a primary indicator to show the effectiveness of the hydronic fluid additive. So testing was done before and after additive dosing, providing a direct empirical support for the improved heat transfer. Again, it should be noted that there were several other thermophysical properties that do act as mechanisms for the increased heat transfer, but here again, we only looked at the surface tension. So this was done by a third-party lab using a Wilhelmy plate method. And then so you could see that for site number 1, the surface tension reduced from 65 millinewtons per meter to 29 millinewtons per meter. Similarly, site 2 reduced from about 49% from 71 millinewtons per meter to 34.5 millinewtons per meter. The diagram on the bottom right shows how the Wilhelmy plate test is performed by essentially measuring the force exerted on a partially immersed vertical plate to determine the surface tension and interfacial tension of that liquid itself. So into the actual discussion and conclusion from what we found from the study. Again, for site number 1, and we found that there was a 10.7% gas energy savings using option C, weather normalized approach. This was due to the metering issues at the retrofit isolation level, being that the boilers, the flow meter data, and also the gas metering data was found to be faulty at that level, so that opted to using the option C. Site number 2, again, resulted in a 19.8% gas energy savings. And this was normalized using the heating load based on the available option C data that was available to allow for normalizing for heating load. And this was able to compare the additive performance at similar outputs for pre and post to provide an apples to apples comparison. Ideally, this would have been done for site number 1. However, due to the metering issues and the switch to option C, it did not allow for a heating load output normalization. So for site number 1, a weather normalization approach was used. Again, there were the trend using the OAT binning analysis shows that there's higher savings trending in lower OAT bends, specifically less than 60-degree temperature daily temperature bends. There was the findings of the study align with the manufacturer's studies, but again, that lacks source data from the manufacturers to be able to cross-validate. However, the findings here do align with the savings claimed by the manufacturer. There were no clear improvements in thermal efficiencies shown at the system that was selected for the study. This is inconclusive due to the system boundaries that were used, primarily including only the hydronic boilers themselves, and not including the heat distribution components, such as the air handlers that were used to distribute the heat throughout the building. So it's unclear if there were thermal efficiency improvements within or outside the system boundaries, but based on the findings from this study, it was unclear if there were any clear thermal efficiency improvements at the boiler level. So relative to standard incumbent water-based hydronic fluid additives, so it should be noted that this study only looked at water-based hydronic fluid additives without water glycol solutions for antifreeze properties. So it was demonstrated versus the incumbent technology that this additive demonstrates superior reduced energy consumption, although the post model showed instability due to that dynamic response. It still showed that the additive showed reduced energy consumption, specifically at lower OAT levels. The primary implementation barriers included the ROI, the minor cost barrier of the ROI less than 3 years for site number 1. Also, there's more uncertainty in colder climates, as these studies were performed in milder climates. So it would be recommended to perform future studies in colder climates to cross-verify the savings provided by the manufacturer in colder climates. And then lastly, one of the product barriers identified from one of the facilities is the product lifetime, specifically site number 2. Their concern was the chemical degradation of the product over the lifetime, and then wanted to determine if there's any impact on performance. So going into the recommendations found from this study, so based on the study's finding, we were able to verify the gas savings, the manufacturer claimed gas savings of 7 to 15% in real-world operational hydronic heating buildings. We were able to confirm the surface tension reduction of about 40 to 50% and successfully low-risk retrofit implementation, so it was easy for each site to install. Further studies, we recommend to expand this field testing to varying climates, again, mild to colder climates, to verify the trend of higher savings at lower OETs. Additionally, we recommend expanding field studies to 5 to 10 additional sites across these varying climates, and additionally across 2 or plus heating seasons to capture full system variations. Going forward, we recommend that data transparency be provided for the manufacturer's source data, and that be used to cross-validate with the study or future studies for this additive. The future studies should definitely address the concerns of product lifetime over multiple years and assess any degradation in performance to determine if the product lifetime can be reduced or extended. And then also, lastly, it's recommended to compare this additive with similar nanoparticle additives designed to enhance heat transfer efficiency that also don't require any major hardware modifications. So with that, that concludes the presentation for today, and I'd like to thank you all again for attending today. I've left a little bit of time for us to do a little bit of Q&A, so feel free to drop any questions in the chat or raise your hand, and I will be happy to answer any questions here today, or if I cannot, I'll be sure to follow up as soon as I can to provide any answers or any follow-up questions. Additional inquiries can definitely be directed towards the program manager, Ava Donald, and she can be able to direct those towards us, and we'll be able to answer those as soon as we can. So thank you. We definitely look forward to continuing the dialogue on this emerging technology. And then we also look forward to seeing all of you at upcoming GET webinars. So thank you.
So Christopher, there's one question in the chat from Noe. Did you test if there was any savings just from flushing the system without the additive before adding the additive?
No, so no, we actually did not, Noe. From my understanding is that the on-site staff simply dosed the system without flushing. So we did not test before and after flushing the system in itself. I think what was assumed in the site recruitment itself is that the systems were well maintained. They were properly maintained by a water treatment company, so that it was assumed that the flushing wasn't required at that point.
So the second question is from Cecilia. How many fluid additives manufacturers are there?
That's a good question. This study anonymizes the additive manufacturers. We did not quantify the number of manufacturers that were out there, but that's something that we could follow up on, as that was not part of the study.
There is at least one other, you referred to it, that does a nanoparticle.
Yes. So the reference to that was really just to the technology itself, and so we did not actually quantify or actually categorize which other manufacturers to include in that, and so that would definitely be something to follow up on as part of a follow-up to the study.
Okay, so the next question is from Colleen. Sorry, I may have missed it, but what did it cost and how long did it take to install?
Thank you, Colleen. So we went over the slide about midway in the presentation, and so I can go back to that. So the cost for the additive itself was obviously determined based on the total system volume, and it penciled out to about $500 per gallon. The installation for the first site was noted to be longer than 10 to 15 minutes, and so based on the volume, it took not too long to install, but longer than expected. So the installation was rather quick.
All right, next one is from Priyanka. Was there any investigation to the energy impact on circulator pumps? And did the additive also affect viscosity and affect pump power?
So there was not any special analyst investigation into the impact on the circulator pumps. We did find that there was a difference in flow rates pre and post. However, that was not something that was specifically identified. It is known that the additive does affect other properties such as viscosity, which could affect pump power. However, we did not measure that as part of the study. Again, we only measured surface tension, which is not an effect on pump power in itself. So we cannot determine it based on what we've found from the study, but definitely something that could be followed up, the effect on pump power and runtime, and then the system components in itself.
All right, next question is from Colleen. Why was it so difficult to find sites?
The requirement that we did for the sites was based on hydronic fluid additive that met specific hardness and iron concentration levels. Also, one of the bigger challenges was finding sites with working BAS systems, primarily with good, valid water flow data, up-to-date, calibrated gas metering data. So some of the sites we came across did not have some of their metering equipment online, and or they were just not willing to participate in the study itself. So another key barrier was that for site recruitment was that there was no verified field studies before this, and so they were a little hesitant to join the study without having seen that this has already been proving at other sites. So now I think that we have shown this is working at real world commercial applications, and I think that going forward, the site recruitment should be a little bit easier.
So the next question is from Jorge. Expanding on sites concerns regarding product life, do we know how long this additive lasts and how many times per year do I have to replace the additive to maintain performance?
Good question, George. Again, this is not something that we addressed in this study. There was concerns about the product lifetime brought up by one of the customers. And so definitely as a follow-up to this, we'd like to be able to perform this over multiple post-additive heating seasons to see if there is any degradation in the performance in itself. Again, due to the limited timeline of the study, we were able to only collect one heating season post-additive, and so it didn't reveal any noticeable degradation of the performance within that year. So based on what we found, we can't determine any, we can't conclude anything on the product lifetime. And also, I think it would be recommended to refer to the manufacturers itself to see how many times per year to replace the additive to maintain performance. That's not something that we categorized for this or quantified for this study.
So Kate, you're going to let Dale make some comments?
Yeah, I think he should be good to unmute himself now.
Yes, hi everybody. Sorry, I was trying not to obviously stick my nose in as the vendor in place, but I wanted to add some comments just based on our work, which, as Christopher rightly said, is outside of the scope of their work. But happy to add some initial comments. In terms of the stability, we have tested durability of the product. It's thermally stable up to temperatures above 140 degrees Celsius, which is 260 degrees. I think Fahrenheit, the product does not degrade thermally in heating or cooling systems. The main consideration is thus losses through leaks, which do occur. And we try and obviously mitigate that through good site selection and working with incumbent water treatment providers. And it's just about understanding those losses and obviously not going into systems that are having active mechanical issues. But the system is clean and tight, it will last forever. And we do have test data from the UK for 12, 13 years of surface tension testing to confirm the presence of the product. And then I think just the only other one is about the viscosity. So the product dosed at 1% has a negligible impact on density and viscosity. It does have a positive impact in terms of effective viscosity, which is more of a shear thinning effect as the water, the flow increases and the water's put under more stress, which actually helps pumps a little bit. But it's not a major, claim that's made by the product. So it's a negligible impact. It's not like glycol where we expect the viscosity to go up by 20 to 30%, and we have to then factor that into our pumping calculations.
So Jorge had a sort of follow up on that. Is there data on impacts to water hardness and or long-term corrosion impacts? So wondering if there's a concern relative to corrosion damage and third-party studies from the UK validating this technology.
Yes, so we've tested with hard and soft water from a corrosion level. The product itself in isolation is less corrosive than water, but not enough to be considered an inhibitor, have inhibitor properties in its own regards, and thus we are not a replacement for your traditional water treatment. So we've done a lot of work with that. We've got boiler and chiller warranty approvals, and we continue to build that evidence base as well. We do appreciate that, sometimes the idea is if it ain't broke, don't fix it, don't touch it. So that's why we do work very closely with the incumbent water treatment providers to give people confidence. And often people try it in smaller sites before building up to larger ones. And then the answer is yes. So we have prescriptive rebates in Canada with Fortis BC, who ran 25 sites under that innovation demonstration program. We have independent studies in the UK with the likes of Energy Saving Trust, and people like JLL and HSBC have done a 400 site pilot that we've reviewed. And in fact, to put him on the spot a little bit, but Michael, who's in the chat, he's done some work for the California Technical Forum in reviewing. We've got 118 different case studies, 692 buildings that have been reviewed. So outside of the scope of the United States, we've got a lot of systems in the UK and in Canada as well, in those colder climates that were questioned in the report. So we're very happy to share those. Some of them are customer led, some of them are independent, and we continue to build that evidence base out, and happy to share that as needed.
So Michael had some separate questions as well. What is the magnitude of uncertainty plus and minus savings associated with the reported saving at each site? For instance, what was the accuracy of the metering used? And then second, what were the average load levels for the boiler systems at each site relative to the system heating capacities?
Yeah, so the uncertainty analysis wasn't included, as we assumed that the existing metering was calibrated and within the calibration standards. So that's assuming within like 1 to 2%. But however, it wasn't included into the analysis in itself. Obviously, for the first site, it was option C, so it resorted to using the PG&E gas metering data, which is assumed to be of the highest accuracy. But again, we would have to get the accuracies from the meter itself, which we were not able to get from the sites. So there was a little bit of a lack of information there, where we could not get the calibration records in themselves, but it was verified that these were calibrated equipment. In terms of the average loads, yeah, I would have to pull that up to be able to verify specifically. But yeah, the load for one system or one site was quite a bit more compared to the other. Being that site number one, it was 7 stories, and so I could follow up with you, Michael, and provide kind of a range of outputs or the load levels that each system was providing for the system relative to the site's size and then the system's heating capacities. So really the only thing that was quantified here was the savings analysis itself, the percentage, and we didn't go to as far as quantifying like a normalized savings per kPTU per the system size, capacities, and such. But I'd be happy to follow up with that for you.
All right. I don't see any other comments in the chat at this point. Does anyone else have anything they'd like to either put in the chat or raise their hands? Okay, Jorge had another question. What was the utility that incentivized this is additive? I could actually probably answer that. Oh, in Canada. Okay. Maybe
Dale.
Dale.
Yeah, I put the link in the chat. It's Fortis BC.
Link, yeah, looks like Fortis BC.
Yeah, so they actually ran 25 sites under their innovation demonstration program with universities, schools, and so a similar project run internally back in 2019. They don't share the report, which is a shame because they have now started sharing reports of their modern work with things like gas absorption heat pumps. But they are willing to speak to individuals, especially at that utility level and that state level. If you'd like to give them a call, I can pass you on to our account manager there.
All right, we've got a few minutes left if there's any other questions that anyone has. I'm not seeing anything. Kate, do you see anything in the Q&A?
Nope, I think we are all good. Nothing in the Q&A. Yeah.
All right. Well, oh no, there's a couple more comments about the price and sync these with GTI lab testing. Actually, we looked at there have been a number of tests done. Curious what you mean by syncing though, just to compare it. The lab tests, as I recall, weren't as clear outcome. Yeah, findings are different.
Yeah, I think
go ahead.
Yeah, the key thing that we want to highlight is the lab test was done in steady state. So it was a constant test with constant loads, which if you consider our product helps make systems more responsive to reduce run times, to reduce back-end wastage and temperature overshoots. None of this is actually captured in steady state testing. And it's often the main disconnect between what you see in a test, especially a steady state boiler efficiency test, heating up a volume of water, and how buildings actually operate in real life. And I think one of the challenges that we are trying to understand or trying to get across to the marketplace is, if you model a system in steady state, it never turns off. And you end up putting a lot more thermal loads into the water than you actually need to provide comfort heating. And that creates the overshoots. So we're trying to really highlight the disconnect between steady state testing and real life operation, which includes the unsteadiness. So that's the main difference. But GTI averaged, I think, about 4% across all the different test runs in boiler efficiency. But we don't claim boiler efficiency. We claim reductions in gas consumption. So they are very definitive, the two different tests.
All right, I'm not seeing any more comments. I guess if there are no more comments to add, then Chris, thank you for your presentation, and we appreciate everyone that's attended and asked a lot of very interesting questions.
Thank you, everybody. Really appreciate it.